So in this video, you will learn the 4 most important questions that can completely change your interview game. Basically, we are going to talk about hashing. And hashing, if you don't know, it is one of the most important concepts in the entire computer industry because every fast access of data happens through hash table, hash set, or some sort of hashing mechanism. On top of that, hashing is really important when it comes to network security and cryptography and secure transactions, RSA tokens, stuff like that. That's why interviewers just love asking hashing questions. I personally have been asked so many hashing questions throughout all the interviews, and it is one of my favorite topics to go to if I have to interview someone. So that's why these 4 are the most popular questions and they are going to really help you out. So feel free to take a look at them. Hope you find them useful. So we are going to solve a very interesting LeetCode problem today called Roman to integer. And if we see some of the popular companies who have already asked this question, there are companies like Amazon, Adobe, Apple, Google, Microsoft, Bloomberg, Facebook, Uber, TikTok, LinkedIn, and Goldman Sachs. So that's why I'm paying my utmost attention. I hope you also enjoy the video. So this is a LeetCode easy problem and also a very valid problem. If we understand the problem statement, it's quite simple. We are given a Roman language number and we need to convert into a decimal system integer. Basically, that's what it is asking. Suppose we are given a value that looks like XX, then in this case, we need to return 20 as the answer because that is what it means in the normal decimal system. Suppose we are given the value of like I, we need to return 3 as the answer because 3 is what represents as I in the Roman numericals. Now we are given a very extensive definition that what every single symbol means and the Roman to its subsequent value, and also what are the different symbols and what are the rules of the Roman language. Now these things are pretty easy to comprehend. There is only a little bit complication when this condition comes in, where it says that suppose a smaller value is placed right before the larger value. In that case, we need to make a subtraction. So I in this case means 1. I is a smaller value and V is a bigger value, which means 5. Now typically if we put any values like Vi, what we are going to do is we take the value of V, so which is 5, and we take the value of I, which is 1. So 5 plus 1, it is 6. So we need to return 6 as the answer. But the thing is, when we are in a condition where the smaller value comes before the larger value, so say for an example IV, this is one of those scenarios. So in this case, actually we are going to subtract the value of I from the larger value, and that is how Roman numerical works. So in this case, the answer is going to be 5 minus 1, so 4. 4 is what we need to return. And there are 6 such cases where these numbers can happen. These 6 cases are, so these are 6 new values that we have been able to identify based on the rule of a smaller value being placed exactly before the larger value. Okay, so I have drawn the value conversion table over here, and now first we will try to understand that how does a numeric system work in the decimal formula. Suppose we are given a value like 1521. How does this value is being generated? Well, this is a decimal format. So in the decimal format, the value is being generated by 10 to the power of whatever the number of values that are present after it, and multiplied by that particular value. So let me explain to you that how does this value has been formed. This value has been formed by doing multiplication of 1 multiplied by 10 to the power of 3, because there are 3 values present after 1, plus 5 multiplied by 10 to the power 2. So if we do sum of these two, we get the answer of 1000 plus 500 plus 20 and plus 1. And sum of all of these is actually leads us to the value of 1521. And this is how this value has been actually broken down. Now in this case, if we see, the largest value is always presented first, then the second largest value, then the third largest value, and then the smallest value. And this is how the numeric system works. Same logic applies to the Roman integer for the most of the parts, and the logic is quite simple. So suppose in the input we are given the value of How do we know that what integer does this value represent? Well, the answer is quite simple. All we will have to do is we will have to see in this table, fetch its value, and then keep adding the values by itself. So in this case, okay, this m is represented by 1000, then this d is represented by 500, then we have x and x. So we know x means 10 plus another x means 10 and plus I means 1. So if we do sum of all of these values, the answer we get is 1521, and this is how this value is being represented. So this seems pretty trivial so far, no issues with this. And also this is also following the methodology where the largest value is present before its small value and before its small value. The problem comes when we have to deal with these 6 items. So let me also draw these ones as well. Okay. Now suppose we are given this as an input, and these are the values that are anomalies in the Roman integer system. These are the values that operate in the same way as the decimal system operates, but when we have a smaller value, so in this case, if you look closely, okay, m is the greatest value and that is why it is presided at the first. D is second greatest and it is presided at the second value. But the thing is, in this case, x is actually a smaller value because x means 10, meanwhile L means 50. So in this case, though x is a smaller value, it comes before L, which means we will have to do a subtraction in this case between these two values and addition with all the values before that. So in this case, let's see what is going to be the answer. So this is going to be m is going to be 1000, then same way this d is going to be 500. That is okay. But when this x and L comes, so basically now what we will have to do is we will have to do minus 10 plus 50. So in this case, the answer is going to be 1540, and this is how we need to represent. So the logic is actually quite simple in this case if we try to understand. What we can simply do is we can simply create a hash map with all of these values combined in a single hash map, and this is going to be the key, and its subsequent values are going to be the values. Now every single time whatever the input we are given, the logic we are going to follow is quite easy. Okay, so for an example, this is the input we are given. Now let's see that using these as the hash map, how we are going to solve this problem. The idea is every single time we will take two values. So in this case, okay, these are the two values. We will try to see that whether they are present as keys inside our hash map or not. If they are present, we directly take its value. If they are not present, we break them down and individually take their values and do addition, and keep doing that till we find the answer. So in this case, first we will try to see that, okay, first two values are md. Is md present as an input? No, md is not present as an input, which means we will have to take m and d separately. So first we will take m, so m's value is 1000, and plus we will take d, d's value is 500. So now, okay, we have taken care of these two values. Now again we will keep on repeating the same process. So in this case, okay, we will take these two xl as 1. So is xl present? Yes, xl is present over here and its value is 40. So we can directly add 40 over here in this case for this xl and directly jump to this I. So okay, once this is done, now we are again at this ix. So again we directly try to see that whether ix is present or not. So ix is present, awesome, good for us. So in this case we can directly take 9, and now we do not have any more values to iterate over inside our input. So we can actually just do sum of all of these values and return as the answer. So in this case the answer is going to be 1549, and this is the whole logic behind our operations. So see, if we just create a hash map with all the possible values, it becomes quite simple for us to solve this problem, and that is why this is a LeetCode easy problem. If we see time complexity, in this case the time complexity is actually going to be big O of n, there where n is the length of all the values inside the Roman integers. But the thing is, in this case the input we are given a finite number. So because it is a finite number, it is a finite time to calculate that. So that's why I'm putting the time as constant, and even in terms of space complexity, apart from using couple of variables, we don't have to use anything. So this is also going to be constant. First of all, we are going to initialize our static hash map and assign all of the values we mentioned. After having all the values, we will start implementing the Roman to integer method. So first we are going to assign some variables. So first variable is sum, the initial value is going to be 0, and we are also going to have an I to iterate over the given input, and initial value is also going to be 0. Now we are going to run a while loop. First thing we are going to check is that if the given I, if is still less than string dot length minus 1. Basically we will first try to check that whether the given string for two values, does its value exist or not. So now we will check that if this two symbol strings, if that is present inside our hash map, we are going to add the value of sum. Also we are going to update the value of I by values of 2, because we are already taking consideration of two values, and then we will move on to the next value inside our loop. And say for example, for some reason that is not the case, in that case all we will have to do is we simply need to add one value. So once our loop ends, we should have our answer populated in the sum variable, so we can simply return sum. And now let's try to run this code. Seems like our solution is working as expected. Let's submit this code. And our code runs pretty fast compared to a lot of other solutions, and it is also very efficient in terms of time complexity and space complexity. So I would be posting the solution in the comments, so you can check it out from there. Thank you. So the problem we are going to solve today is called copy list with random pointer. And if we see some of the popular companies who have already asked this question, there are companies like Amazon, Facebook, Bloomberg, Microsoft, Apple, Adobe, Google, ByteDance, eBay, and Uber. So that's why I'm paying my utmost attention. I hope you also enjoy the video. This is a LeetCode medium problem and a very well-liked problem. Basically in this problem, we are being asked to copy a linked list. The thing is, this linked list is actually kind of a tricky linked list. It's not your common linked list. So if we know by a definition, the linked list that we understand has a structure that looks like this. And the last pointer points to a null value. So this is a typical structure of a normal linked list. But the linked list that we are given in this case is actually kind of little bit of tricky. It is a linked list that looks like a structure that is something like this, where in this structure we have these two parts common. So the green values over here are defined as the regular linked list pointers, where we have a value and we also have a pointer that refers to the next item inside the linked list. The thing is, at times we are also given these random pointers in our linked list as well, and the purpose of these random pointers is that they can point to anywhere. And basically we need to keep track of all of this, and on whatever the given linked list that we have been provided, we need to create a deep copy of that particular linked list. So this is what is being asked in this problem. Like if you cannot find, or if you try to understand, you can read this problem statement again by pausing the video right now, or you can see some examples that I have shown over here. So let's take a look at the first example. As I was mentioning, that this is not your typical common linked list. You see, in this linked list, we are given one value for every single item. But thing is, with this value, rather than having just a single pointer that points to the next element, which is defined over here as this next pointer, we are at times also given this random pointer as well that can point to any direction, and we need to keep track of that, and we need to create an exact copy. So inside the input, we are only given the head of the linked list, and this is the original linked list structure behind the scenes. And in the output, based on this given head value, we need to iterate over this entire linked list, and after iterating, we need to create an exact copy of it. So if we see some structure of this given linked list, it is going to look somewhat like this. So in the output, basically we need to we are initially located at this position. This is the head of the linked list, and we need to find a way to iterate over this entire linked list in the exact manner and create a deep copy. So what does creating a deep copy means? Means that if some node does not exist in our copy, then we would create a new node, take all of these values exactly as mentioned, and put these values inside our new node and mark it as the node in our sequence, and then in the end we need to return the newly created linked list. So basically we are going to create like 5 different nodes. Every single node is going to look pretty much similar to this, and they are all going to have a structure that is common over here, and basically we are going to return this as the answer. So this is the whole ask. There are few other examples given as well, but they are not as important. They are just kind of simple. So I think you get a general gist of what are the things are being expected. Now we have already done similar questions like this, and even say for an example, if this was just a random linked list, it would have been too easy for us to solve this problem, because what we could have done is we initially start with the first position, so with this head position, and just keep on creating a new linked list based on whatever the values we are iterating over right now, because we have a very certain path in any linked list where the first node is the value, so we can just copy whatever the value this has. So say for example, this has value number 5, we can just copy this value as value number 5, and this has value number 6, we can also copy value number 6, and if this has value number 10, we can also copy value number 10. So these things are easy to do. It is also easy to iterate to the next node inside the linked list, because we are directly given the pointer, and using that we are also going to do the same thing. And basically in the end, when we reach to the null value, we have reached to the end, and simply we can return this as the answer. Now copying is not as simple in this case, because we are dealing with a structure that looks like this, where there could be potential possibility of cycle. What do I mean by potential possibility of cycle? Say for example, we are given these two nodes, the values are 7 and 8, and we know for sure that this node is going to point over here, and this node is going to point to the null value. These two things are fact, but it could be possible that these two random nodes, so this random node points over here and this random node points over here. Now if we try to iterate over this, like a different version of this linked list, what is going to happen is that, okay, currently we are located at this head value. So what would happen in these cases? Well, the thing that would happen in these cases is that over here, rather than coming back to this point, we might end up creating a whole new node with the same value 7, and we will try to iterate over this value. And this over here again, for this particular 7, the value is pointing towards 8, so we might create a new node 8, and then we keep on repeating. So basically, because there exists a cycle over here, it is possible for us that while creating the copy, we could end up in an infinite loop, and that could be disastrous. So we will have to avoid that in any single cost. Okay, so say for an example, this is one of the input that we are given, and we are trying to convert this and trying to create a deep copy of this. Basically, we are given this as the head node, right? And now we need to iterate over this one. Now, but the thing is, in this case, if you see, there is the cycle present amongst these random nodes. So this is a cycle, and if we don't take care of it, we will actually keep on ending it in an infinite loop. Now the thing is, in order to detect any cycles, we actually have a great way of doing it in all the graph problems, right? But the thing is, you would say that why am I mentioning graph over here? Because clearly this has been shown as a list or a linked list kind of a problem. The idea is that rather than treating this as the linked list problem, we can actually treat this as a graph problem, where every single items can be treated as the form of vertices and edges. Because remember, in the graph, the two most important items are vertices and edges. So for the vertices, we can actually consider these input nodes of the linked list as the vertices, and for the edges, we can actually consider these like next edges, so the white edges and also these purple edges, to be considered as the edges. Now in this case, the edges are going to be directed and also unweighted. Now after doing this, after treating this and trying to consider this as graph, things becomes much easier for us to keep track. Why? So I have actually drawn this figure where I am visualizing this given input as a graph. Now in this case, if we treat this as a graph, it becomes very easy for us to copy and maintain. Why? Because the logic we can use in this case is that any single node, we can actually create a visited directory or a hash set or a hash table where we keep track of all the nodes that we have visited so far. So that way it is going to be great for us to keep track of everything. And once we are done with all the nodes, we can simply return the copied nodes. So the logic we are going to use is, okay, let me make this a little bit smaller. Okay, so now let's try to iterate over this given node, and we will start iterating through its head. So this is the head pointer, and every single time we are going to keep the same logic that we use in any single graph problem. That first we will check that whether that particular node has been visited or not. If it has been visited, we will skip it. If it has not been visited, we will add an entry over here and we will create its clone node, and we will keep on repeating the same process. Now for every single node we have its edges. So basically we are going to go in depth first search manner, and in depth first search manner we are going to go over all the neighbors of any single node and keep on repeating the same process. And also because we are repeatedly doing the same thing, we are actually going to do this recursively. There is also an iterative way to doing it, but the thing is I like recursion better, so I'm just going to show you the recursive way. But remember, there is also an iterative way. And if we see this diagram, basically there are just few functionalities. So these white edges, they refer to the values of the next pointer, and also these purple edges, they refer to the values of the random pointer. And let's start iterating. So first we are at this head pointer, so we are at this node number 7 is not present inside our visited hash set. So first we will add an entry 7 over here, and now let's just create a new node called 7. So we will create a new node. Okay, 7 has been created. Now what is the next node of the new node? This is the random pointer. So where the random pointer is pointing towards, it is pointing towards null value. So if it is pointing towards the null value, we do not need to add it to our visited set, because remember, null is not a new node, but it's just like the end of the list. So we'll just keep track of it. So okay, this one is like the null. And also if we see in this case, the next pointer we need to go over is the next edge. So next edge is pointing towards value number 15. So we will check that whether 15 has been visited or not. 15 has not been visited, so we will add entry 15 over here. Now we will start visiting the 15's first edge, which is the random pointer. So if we go depth first search recursively, okay, so this 15th random, so let me just create a new node 15 over here, and this 15th random edge is taking towards node number 10. So 10 has not been visited. We will add an entry 10 over here, and we will also create a new node for 10. And in this case, the 10th next node, or the node in sequence, is the random pointer. So random pointer is pointing towards 13. So 13 has not been visited, so we will go over 13 node. So we will create a new entry called 13 over here in this case. Awesome. So now we have all 4 of our nodes set up, and we have also iterated towards the random pointers. So now at 13, when we iterate over the random pointer of 13, it takes us back to the node number 15. And because this is taking us back to the node number 15, which means we will check that, okay, whether this has been visited or not. Yes, 15 has already been visited, which means we are in a cycle. So we need to break out from there. So basically we do not care, and we will not get ourselves involved in this one, because we have already created a copy of 15. So because we have created a copy of 15 in this case, so rather than creating a new node for this particular random node, we will simply point it towards this 15 that we had already created. And that is how everything is going to work. And then we basically have taken care of this cycle without getting secluded in the infinite loop, because we use the visited hash set. And then for every single node, there is still the next node remaining that we need to traverse over, which is simple to do, because for next node it is only pointing towards the next node. And in this case, from 15, after completing this sequence, when we go to the next node, okay, this one is pointing towards value number 13. We already created a new node, so we do not need to create anything. We simply need to add the entry over here to point it towards the correct direction. Same way 13, next node is going to be 10. That is also good. And in the end, this 10 is going to point towards the null value. And this is how our traversal is going to be completed. And we would have created an exact deep copy of this particular linked list with random pointers without doing any extra work. And this is like a wonderful approach. So all we did is we treated linked list as graph. And this is a great way to understand that how can two different data structures can be interchanged, and we can use trick of the one data structure in the other data structure. So I know this was a little bit complicated to understand, but if you just like try to put some thought behind it, things would make much more sense. And if we see time and space complexity, in this case the time complexity is actually going to be big O of v plus e. So v plus a is the number of vertices plus edges. Why? Because this is a graph problem, so this is what we have to deal with. And in general, in this case, rather than treating it as v plus e, we can actually treat it as big O of n, where n is the number of nodes given in the input. And in terms of space complexity, in order to use the recursion, we will have to use big O of n space. So this is a decently good time and space complexity. Well, I just need to make a quick remark. If we use the iterative approach, the space complexity would become big O of 1 in that case. First of all, we are going to create our visited hash map, and inside our hash map, we are actually going to do things a little bit trickily. So as its key, we are going to keep the values of the old node, and as its subsequent value, we are going to keep the newly generated copy that we have created. So at any given moment we encounter any already visited node, we can simply return its copy rather than creating a new node every single time. So this copy random list method is also going to be our recursive method. So first we will create a terminating edge case that if the given head is equal to null, we can simply return null. If that is not the case, first we will check that whether the current head value we are at, has it already been added to our visited node. And if it has been visited, we are simply going to return the subsequent reference value that we have stored inside our visited node hash map. If, say for an example, this has not been visited, so in that case we will have to create a new node. Now as a new node, we are assigning it to the value of the current head value that we have received as an input, and as its random pointer and next pointer, current values are null, but we are going to populate these. Now once this has been done, since this is a new node, this needs to be put inside our inside our hash map. Now notice in this case, the head is the existing node that we are taking as an input, and this node is the new node that we have created, which means we are storing the copy as the value inside our visited node hash map, and as a key we are using the older value. So now for this particular node, we have taken care of the value of that particular node. But the thing is, we haven't taken care of the next pointer and also the random pointer. So we will do that. In order to do that, we will actually have to call for the next pointer, we will actually have to call head.next value, and we will have to call our recursive copy random list method again. So let's do that. In same way, for the random pointer, we will also have to do the same thing. Basically, once this has been completed, we simply need to return the node. Let's try to run this code. It seems like our solution is working as expected. Let's submit this code, and our solution runs pretty efficiently in time complexity compared to a lot of other solutions. In terms of space complexity, there can still be improvements made, but I guess you can figure that out. I'll be posting this solution in the comments so you can check it out from there. Thank you. Keeping with that goal in mind, today we are going to do a very interesting LeetCode problem called first missing positive. And if we see some of the popular companies who already asked this question, there are companies like Amazon, Microsoft, Google, Apple, IBM, TikTok, Hudson River Trading, ByteDance, Twitch, Facebook, Uber, and Snapchat. So that's why I'm paying my utmost attention. I hope you also enjoy the video. So this is a LeetCode hard problem and also very well-liked problem on LeetCode. Basically, we are given an unsorted integer array called nums, and we need to return the smallest missing positive integer. So the problem statement is really small and easy to understand. The tricky part in this problem is that we are being asked to solve this problem in big O of n time with a constant extra space. So time complexity has to be big O of n and space complexity has to be big O of 1. So this is the difficult part that we are trying to achieve. Now first let's try to understand this with few examples that what does this problem is asking us to do. So in this case, we are given a numbers array, and in this case the values are these. Now we are trying to find the first missing positive number. Okay, now what is the first positive number? First positive number is going to be 1. Then what is the second positive number? It's going to be 2. What would be the next one? It would be 3. Now in this case, since 1 and 2 both are present, 3 is the first missing positive number, so we need to return 3 as the answer. If we take a look at the second example, again in this case we have 1 present, but we do not have 2 present. So because 2 is going to be the first missing positive integer, so in this case we don't even need to check for all the remaining ones. 2 is going to be the answer that we need to return. And same goes with this example. In this case, since we don't even have 1 as the answer, we are definitely going to return 1 as the answer because 1 is the first missing positive number. Okay, so the problem statement is really easy to understand. Now let's see that what could be the possible different approaches we can take in order to solve this problem. Well, the first approach that comes to our mind is a brute force approach. In the brute force approach, what we are going to do is we will try to find the first positive number. So first positive number is going to be 1. We will see that whether 1 is present in this or not. Okay, so 1 is currently present. So now we will move on to 2. 2 is also present. So then we will move on to 3. So value number 3 currently is not present. So we can say that 3 is the first missing positive number, and we will return 3 as the answer in this case, right? But the thing is, what is the issue with this brute force approach? Well, the issue is quite simple. Time complexity is actually going to be big O of n square, which is disastrous. So we will have to do something better than this. Let's try to find another approach and see if we can do something better. So say for an example, suppose this is the given input. The idea is that if for this given input, if we somehow sort this input, we would actually able to do something better. So let's just see the sorted result. All we need to do is go to the first positive integer. So in this case, first is 1, 1 is present over here, and then move to all the other elements until we find a place where the next element is missing. So in this case, we can clearly see 3 is missing. So 3 is again going to be the answer for the sorted approach. So sorted approach works better than the brute force solution. But the issue with the sorted approach is that from given input, in order to generate the sorted array, it takes us the time complexity of big O of n log n just to generate this sorted approach, and then we will have to iterate over it once. So the thing is, this time complexity is still more than what we want. So this approach is also not going to work. Let's try to see some better approach. Okay, now before we go to the next approach, first let's try to make things much easier to understand. Suppose if we are given any input, and if all the values are starting from 1, only positive values that are incrementing in sequential order, what would happen in this case? What would be the first missing positive in this case? Well, definitely the first missing positive in this case is going to be value number 5. Why value number 5? Because currently the given input n only has 4 characters, and all the characters are like 1, 2, 3, 4. So the minimum possibility is that the value could be 5, or it could be any single value from starting from 1 to 4. So basically all the values that are concerned of us is that the first missing positive will only be between the given n plus 1. So from 1 to n plus 1 is the possibility where the first missing positive value lies. In any other values are no use of us. So say for an example, if we are given input n where the values are such as like -1, -6, then +8, then 1, 2, something like this. If this is the possibility, definitely the first missing positive in this case is going to be value number 3. But the thing is, since here there are only 5 values, the first missing positive number can only lie between the values of 1 to 6, nothing more than that. So if that is the case, why are we even concerned with all the values that are not between 1 to 6? If say for an example, values like these 3, we are not concerned with them. And I already explained you why we are not concerned with them, because we are actually going to use it in one of our next approaches. So say for an example, if this is the input we are given, previously for the sorting and also for the brute force, what was the issue happening? The issue was happening that if we want to search that whether value number 1 exists inside this given input or not, it was causing us a lot of time. So what if we speed up this process? We can actually speed up this process by creating a hash map. And what would we do inside this hash map is that at any given position, we will first try to identify whether 1 exists or not. And 1 is not, if 1 is not existent, definitely we are going to return 1 as the first missing positive. That is going to be our answer. That is going to be the most simple case scenario. But if 1 is present, then we are guaranteed that the value of first missing positive is going to be between 2 to 6. So any value that does not lie between the values of 2 and 6, we can simply denote their value as 1 inside our hash map, and then we will do something tricky with our hash map. So let's apply this logic to our hash map. Let me quickly draw the hash map from given input. And by the way, For any particular value, this is going to be the key, and its subsequent value is also going to be same, except for these three values where the value is going to be 1. This is the hash map we have been able to generate from our given input n, where the key is the same value as the values inside our array, and its subsequent value we have done some modification, and all the other positive values, they are equal to whatever their subsequent values are. Now all we need to do is, we know that the answer could only be lying between 1 to 6, nothing more than that for the first missing positive. So we will run a loop starting from value number 1 to 6, and we will try to see that whether all the values between, like including 1 and 6, between 1 to 6, are they present inside this hash map or not as key. And we would be able to do this in constant time, because that is one of the property of the hash map, and that is going to make our lives much more easier. So first we will try to see that whether 1 exists inside the hash map or not, and definitely 1 exists over here, so we can simply go to the next element. So we will check whether 2 exists or not. 2 also exists, so we can simply go to the next element and we will check whether 3 exists or not. Since 3 does not exist inside the hash map, we can immediately say that 3 is going to be the answer that we need to return. And this is a very good approach. This solves a lot of our problems that we were facing in terms of time complexity. Why? Because it takes big O of n time to generate this hash map. Okay, so in order to generate the hash map, it takes big O of n time, and then in order to run this loop and to come up with the answer that whether the value exists or not, that also takes big O of n time. So if we see time complexity, basically we have been able to complete this problem in big O of n time, and this is going to be great. This is a wonderful result, and any single interviewer would be more than happy with this approach. But the thing is, in this problem, if we see space complexity, this is where the problem lies for this approach, because space complexity in this case is also going to be big O of n. Why? Because we are creating an additional hash map. Meanwhile, we are explicitly told that we need to complete this in big O of 1. So can we do that? And the answer is yes. Okay, now let's see that what would be the optimal solution where we also do constant space complexity in order to solve this problem. The logic we are going to keep are same, that any values that are too great or negative or 0, we are actually going to convert them to 1. Now let's see that in this given input, how many elements we are given. We are total given 8 elements, which means that the answer has to lie between 1 to 9 for the first missing positive integer, which means any value that does not fall in this range, we will actually have to change it to value number 1 inside this given input. So let me create a new array. This is the new array we generated. Now let's do a quick recap. Basically, we first check that whether 1 is present or not. Since 1 is already present, we iterated over this given input array, and from that we converted this for all the values that were not falling between the values 1 to 9. Okay. Now we are going to do things a little bit interesting way. What we are going to do is, since we already know that 1 is present, which means we are not worried about value number 1. We are simply going to iterate over this values whenever we find a value that is not 1. A value that is not 1, which means, say for example, we find this value number 5. So we will go to its subsequent index. So in this case, we will go to index number 5, and whatever the value is, we will just convert it into negative. Nothing more than that. This is a very simple approach. So let's just quickly do another array, and we will follow the methodology I mentioned. In this case, the first value is 5. So because first value is 5, we will try to find subsequent value and convert it into negative. So this becomes negative 3. This is value number 1. So we don't need to do anything. Again 1, again 1, and again 1. So since these 4 are 1, we are not going to do anything. Now this value is negative 3. So because this value is negative 3, we will go to third index, because this used to be a positive 3 value. And remember what I said, anything but 1. So in this case, we will go to this value and convert it into negative as well. So this becomes negative 1. Now we are okay. Again, this value is 1, so we don't need to do anything. This value is plus 2, which means we will go to second index and convert it into negative. Awesome. Now, what are the things we have been able to dictate? We already know that 1 is present, which means that the answer has to lie between the values 2 to 9. Now in this case, since we will start iterating over from value number 2, to all the values remaining inside the given input array, because we already know that 1 is present. So we don't need to do anything. And now all we need to do is to check that whether that value is negative or not. And the moment we find the first positive value, that index value is what is going to be the first missing positive integer. Yes, this is the whole logic. Now in this case, since this is -1, this is -1. So these two values we have been able to dictate that why they have been turned into -1, because that subsequent values were present at some point inside the given input array. That is why we converted them to -1. So we can ignore these two. For this particular value number 4, this is a positive value. The moment we identify a positive value, this can only remain positive if there was 4 nowhere to find in this given input. Say for example, we found that this value was 4, then we would have definitely converted this to -1. But the thing is, we did not find anything, and that's why we left it as positive, and we have not been able to find 4 as the first missing positive. So we need to return 4 as the answer. And this is the optimal solution. If we see time and space complexity, in this case, the time complexity is actually going to be big O of n. Why? Because first of all, it takes big O of n time to generate this, and then it takes big O of n time to find the first missing positive integer. So we are satisfying on that aspect. And if we see space complexity, well, apart from using couple of variables, we are not using any additional space, because all of these things are being done on the given input array nums. We are not creating an additional new array. This is a very good time and space complexity and a great approach to solve this problem. Because if you see in this problem, what are all the things we have been through? We first saw the brute force solution, then we saw the sorting solution, then we saw a hash map solution, and then we saw the optimal solution. So we actually went through 4 different approaches, and every single time we started to improve upon something. And this is what any single interviewer would want to see, that how you have been able to do things. And that is why FAANG companies love asking this question. So now let's move on to the coding. So for the given input, first we are going to check that whether 1 is present or not. If 1 is not present, we are simply going to return 1 as the answer. Okay. Now the logic we are going to apply is that any single value that is not falling between our given range, we are going to convert it to value number 1 inside the given nums array. Now all we need to do is we will need to go over the given input array where we have already changed the values with 1, and anytime we identify the value is different than 1, we will go to this array and change its subsequent index location to a negative value. Okay. Perfect. So now with this loop, we have been able to convert all the values to the negative value wherever we find a subsequent positive value, any value apart from 1. Okay. Now all we need to do is run a for loop from int I is equal to 1 to the last element. And we simply need to check that at any given position, if we identify a positive value, we are simply going to return that index character, and that is going to be the answer. Now we are also going to check for a couple of edge cases as well. Somehow if we are not able to return the answer, which means we have found the perfect sequence, so we will need to return the last value inside our first missing positive integer, which is going to be n plus 1. And this is the whole code. Let's try to run this code. Okay, seems like our solution is working as expected. Let's submit this code. And our code runs 100% faster than all the other solutions, which means this is a great solution. And I will be posting this in the comments so you can check it out from there. Thank you. Today we are going to do a very interesting LeetCode problem called word ladder that has a real life application, because this is a game by itself as well. And if we see some of the popular companies who have already asked this question, there are companies like Amazon, Bloomberg, LinkedIn, Microsoft, Google, Uber, Apple, Facebook, Lyft, ByteDance, and Goldman Sachs. So that's why I'm paying my utmost attention. I hope you also enjoy the video. So this is a LeetCode hard problem and also a very well-liked problem, which is a rare combination to be seen. Now in this problem, we are given 2 words, a begin word and an end word, and we are also given the list of words called dictionary or word list. Now our aim is to reach or go from the begin word to the end word by a transformation sequence. The question is, how does this transformation sequence works? Well, the transformation sequence works is that suppose we are currently at word 1, we can only jump to word 2 if the difference between the characters is only 1. So say for an example, if we are given a word like cat and we are given the second word like cot, we can go from cat to cot because there is only difference of a single character a. The c and t are common across both the words, so this is a valid transformation sequence. The idea is that from the begin word we need to keep on doing the transformation sequence amongst many different words, and our aim is to reach to the end word somehow. And if we are able to do it, we need to see that what is the minimum number of ways we can do it, and these words, they has to be present inside the word list that we are given. So we cannot just create words out of fly. This is the purpose of this word list set that we are given, bunch of different words. And if somehow we are not able to reach to this end character using the transformation sequence, we need to return 0, and if we can, we need to return the minimum number of hops needed to reach to there. So let's try to understand this with a couple of examples. If we see this first example here, the begin word that we are given is called hit and the end word is cog, and these are the different words that we are given. So one of the ways we can solve this problem is by creating a word sequence that looks like this. In this case, we are starting from the first word and we are reaching to the end word, and these are all the different hops that we are making using the transformation sequence. So this is a valid example, but if we see in this case, we are actually taking 6 different hops to reach to the end word. Can we do something better? And the answer is yes. There exists a better solution for this problem. So let me quickly show you the better one. Again, even for this example, we are able to reach from this beginning word to the end word, but in this case, we are doing the whole journey by only 5 different hops. So in this case, we need to return 5 as the answer because we are only taking 5 steps to reach from the first word to the end word, and this is going to be our word ladder. If we take a look at the second example, in the second example, the word we are given is hit and again end word is cog, so that is true. But the thing is, in this case, we need to return 0. Why we need to return 0? Well, because this cog is actually not at all present inside this word list that we are given. So since the end word is not present, we cannot reach the end word. So basically we need to return 0. So I hope this explanation makes sense and you are able to understand the problem statement. Now let's see that what is going to be the approach we will take. Okay, so before we come up with the optimal solution, first let's see that what kind of pattern we can see in this problem. Basically, we are given a beginning word and an end word, and we are told that there are some series of words that we need to go to in order to reach to this end word, and we need to return the minimum sequence possible, right? The thing is, in this problem, we are not only guaranteed to given all the words that would be used between this beginning and end word, and it could be possible that we are given some different words that are not being used, or they can be used, but the thing is that leads to like a longer answer, and we do not need to like go through all of them, and we only need to find the shortest path. Now if you see this kind of structure, what does this reminds you of? Well, you are absolutely correct. This is actually a very similar structure to a graph, where you can see the words that are given, they can be treated as different nodes, and the relationship between these nodes can be treated as edges. So we have our vertices and edges, and we have a way to define edges. Now how does a vertices connects to an edge? A vertices connects to an edge through the mechanism that the number of characters of word 1 and word 5 in this case, they only have one differing character, and that's it. That is the only way we can define a relationship between them. Once we have a structure like this ready, now let's see what is our aim. Our aim is to find a path from the beginning word to the end word, and if we want to find the path, what we can do is we can simply iterate over the given input and see that what are the different paths we can take, and try to find the most optimized path or the shortest path that leads us to the correct answer. So in this case, we can actually find 2 different paths that leads us to the answer. First one is the one that I indicated in blue, and second one is the one that I indicate in this purple color. Now in both the cases, this path is actually the shortest path that leads us to the answer, and in the end we need to return the distance between the words amongst these paths. So in this case, the answer is going to be 5. But you get the idea that basically we can, if we are able to generate this graph structure, then all we need to do is just we need to do the breadth first search traversal. And the question is, why breadth first search? Because we are trying to find the shortest path, and if we do depth first search, it could be possible that in practice it might take us longer. So breadth first search would be a better candidate in this case. So if we are able to create a graph structure, and if we do the breadth first search, we can actually find the shortest path. Okay, so now we are going to use the same example that we have been given as the input. Now, first of all, we need to find that the beginning word that we are given is the word hit, right? And say for example, we devise some mechanism to easily traverse through these words to make sure that whether these words exist or not, right? Now the question is, from the hit, we are treating this hit as one of the nodes, right? Now we need to find that what are all the different edges this hit is able to connect to. The idea we can do is that we can see all the possible words that this hit can have with just one differing character. The logic is we can start with the first character and keep all the characters from A to Z, and then keep the remaining two constant. So what we will do is we will try to check for the words such as AIT, then BIT, all the way up to ZIT, right? These are all the different words we can make. Then same way we can keep the H and T common, and then do A, B, C all the way up to Z, and we can keep on repeating the same process. So basically at every single word, what are the different possible words we can have? Well, say for example, if the length of this is equal to M, then basically we can have M multiplied by 26 differing characters and or differing word possibilities. Now amongst these 26 word possibilities, all we need to do is we only need to find the words that exist inside this word list. And since this is a dictionary, basically we can access pretty fast and check that whether any word exists or not. We can do it in constant time. So this is not going to be an extra overhead. So by using this logic, we are actually able to generate all the graph pairs for our given input. So first value is going to be hit, and now let me just quickly draw the graph structure. Okay, so we can actually make a structure that looks like this, and this is a pretty decent representation of the input that we are given. Now this is going to be our start node, and this is going to be our end node, or the beginning word and the ending word. Now basically we need to iterate over the given graph, and we are also going to keep track of all the nodes that we have visited so far. That is to not end up inside any like unexpected loop or infinite loop. Now all we need to do is from starting point, we already mentioned that we are going to run a BFS, and we are also going to have a variable called min that is going to keep track of what is the minimum path we have found so far. So if we just see the input, one of the path we can take is that we start from hit, and then we can go down this path, and eventually we would be able to reach to the end word. So in this case, if we see, and definitely we are going to keep track of all the visited nodes, and everything is going to be taken care of. If we see this path, basically it is going to take us 6 words, and currently this is the minimum value we have because we haven't identified any other path, right? So 6 is the correct answer. Now let's see that if there is any second option that we are missing. So yes, there is another option that we are missing, and the option is that if we start from this hit, we can go down this path, and through this path the number of words we encounter is actually 5. So because we are encountering 5 words, basically we need to update the minimum number of answer we can get. Let's see if there is any another path that we can take that we are missing. And yes, there is also still one more path that we haven't taken, and the path that looks like this. And in this path also we are encountering 5 words. So again the answer is going to remain 5, and we have explored all the possibilities. So in this case we can simply return 5 as the answer because that is what we need to create. And you see, once we have this graph kind of a structure ready, things becomes much easier to comprehend, and we can simply return the answer pretty fast, pretty efficiently. So this is the whole logic behind this problem. Now in this problem currently we are only going in just one single direction, but in practice there can be like a bi-directional BFS where we start iterating from here and we also start iterating from here, and we can do like BFS from this direction, BFS from this direction, to reach somewhere in the middle and to find the answer. And we can do things slightly faster in that cases, but I don't think anyone is going to expect you to do this in any of your interview, so don't even bother. If we see time complexity, in this case the time complexity is actually going to be big O of m. So m is the number of length of any character, and I mentioned that length is going to remain constant amongst all the word list characters, so we don't have to worry about that. So number of m square. Now why m square? M square is taken in order for us to generate this graph like structure. So it takes big O of m square time, and for every single character there can be one possibility that we need to iterate, because we know the starting and ending point. So basically it's going to be m square times n in terms of the number of time complexity, where n is the total number of words given. And if we see space complexity, well, basically we are anyway storing this graph like structure, and that is going to give us like big O of m square space, so we also need to take care of that. So in my opinion this was a tough problem, but once you know the logic you can solve it easily. And this goes to show you that if you know the logic about different data structures, things becomes much easy, because this word ladder game is actually a real life game that people use and people play. So yeah, this is not just a random out of the blue question. Now let's move on to the coding. So since this word ladder problem was already becoming such a big video, so that's why I'm just going to explain you the code rather than typing all of it, and I will go through the explanation. So first of all, we are going to initialize a variable to note down the word length, because that is pretty important. And we are also going to initialize our hash map that contains the information of all the combinations inside the dictionary that could be possible. Now what we are going to do is, for every single word that is present inside this given word list, we are basically going to iterate over all of its characters, and we will try to see that for all the differing characters, what are all the transformations possible. And whenever if a transformation is possible, we will basically add it to our all combination dictionary. Because this is a hash map, inside the key we are going to store the value that is being present and inside the word list, and as its subsequent value we are going to have a list of all the possible combinations that any particular word can have. So this is going to give us our dictionary, and this is going to take basically m square time to do it, or l square time to do it. Now in order to iterate over the breadth first search, we are going to have our queue where we will keep on adding, or we will begin with the first word, and we will not rest until we have iterated over all the neighbors of this first word, and we will keep on repeating the same process iteratively. So we are not doing recursion. We can do recursion, but we are doing it iteratively. And also as mentioned that because we do not want to get inside a position where we end up in any infinite loop, we are basically going to initialize a hash map. And now we are going to basically put the first word or the begin word that we are given as the input, and then we will start iterating over our given queue in the BFS fashion. So first of all we are going to create a pair, or so first of all we are going to remove the node in that is existent inside the priority queue, and then we will try to get its word value. Then we will see that what level it is, and basically we will iterate over all of the different possible words that can be present, and we will keep on repeating the same process for all the adjacent words. And every time we go to the new level, we are basically going to increase the size of the level. So this is going to return us that how many different paths that we have taken so far. And somehow if we get out of the loop, then basically we need to return 0. So this is the whole logic behind the whole problem. And this condition refers to if we have reached to the end word, and this condition refers to in the scenario where we have not reached to the end word, we are somewhere in the middle. So basically we are going to add a new entry inside our queue and we are going to increase the current level we are at. So I think this solution makes sense. I would be posting this code in the comments, so you would be able to check out the code. Don't worry about it. Let me try to run this code, and our solution works as expected. Let's submit this code. And our code runs decently efficiently in terms of space complexity and time complexity. Both are really good. And this is the BFS solution from the LeetCode.